Oh, that's fine. I'm gonna ask you. I'm Patrick. I'm a prof of medicine, but also I work a lot and mostly on machine intelligence. I work on artificial intelligence applied to bionic body parts, how you might connect a robotic device to the human body. We can talk about that later if you want. But today I really wanted to, especially because I think, again, this is the topic I've had in my mind all week. There's a lot of resurging interest in reinforcement learning through trial and error, machines that can actually learn from their own experience in the world. There's a lot of new interest after recent events like the DeepSeek paper that came out, which showed you could use reinforcement learning to turn these like large language models into things that can do chain of thought reasoning for a lot less money than you might expect. So anyway, I thought it's topical that I could bring up the idea of reinforcement learning. We can talk it through. We can try to, again, debate together at the end a little about reinforcement learning, but it's a shorter presentation, and I have one demo. I had tried to have 2 demos for you today, but I realized this is a different laptop and I don't have all the code installed for the second demo. So you get 1 demo today, but we'll walk through it. Cool. So I'm going to tell you a little bit about reinforcement learning, and as promised, without the math. But just so I know whether or not you actually wanted the math or not, you don't get it anyway. But if you did want it, what are your fields? What are your fields of background? Where do you?
That's okay. She's a high school student.
That's fine.
So she is here because she's interested. She's my sister, so I should stop by.
Well, yeah.
I want to study law.
Law, okay.
Yeah, that's what I was thinking.
Okay, well, that's really handy. Like when I try to share stuff in Kim's class, I always want to make sure that I'm trying to connect to things people are interested in, they actually care about, and not just like, I'm going to show you some math on the board or whatever it is. So like looking at some kind of future in legal pursuits, that's really cool.
Yeah, and I'm in my last year of biology.
Okay.
My major is biology, and my minor is psychology, and I do research in cell bio.
Cool. Oh, sorry, what are your names right there? I forgot.
Alma.
Alma?
Yeah, I'm Janine.
Janine? Okay, excellent.
My name's Faisal. I'm in my last year as well, but I'm in accounting.
Okay.
And also was pretty interested in the whole machine learning. I was like, might as well show up, see what it's all about.
Yeah, there's a lot of trial and error learning and generally applied accounting principles, so that sounds, yep, the very gap lecture today. Cool.
Yeah, my name is Don, and I'm doing my Masters of Medicine, and I finished my MD and from Sri Lanka and came here as a master's student, and now I'm in the final semester, and this is my last course.
Okay, wow, very nice. Good choice, good choice.
Hi, I'm Jessica. I recently graduated actually last year in psychology, so right now I'm just taking a gap year doing research in stroke, so yeah, just here to learn.
Neat. Oh, it's interesting, like you see, I mean, like my colleague Rich Sutton, who I'll reference a few times, like has very deep roots in psychology. Like I think we see some nice crossover, especially in psychology and with the reinforcement learning endeavor, and there's some of the really cool trial and error learning results from humans, especially, and animals and other animals that cross over. Okay, so that's very cool. I know Kim, of course. We go way back. Thanks for having me back again, by the way. I appreciate it. It's always a treat to come and hang out. And thanks for switching days as well. That worked out a lot better. Tuesday was quite the thing. Cool. I can tell you later. I was dressed up. I had to prepare to dress up like an archaeologist to like unpack a scholarly piece of literature on camera. Anyway, it was quite a thing. We'll talk about it later. Okay, so before we start any of the talk about reinforcement learning and AI, I'd like to ground most of our conversations in what is this intelligence thing that we're talking about? We should all hopefully have at least a shared understanding while we're chatting today, and then you can go and use whatever definition of intelligence you want to use in your other regular life. But today, I like to, if you'll humor me for today, I'd like to go back to McCarthy in 1953, coined the term artificial intelligence. So John McCarthy stated that intelligence is the computational part of the ability to achieve goals in the world. Now this is I love this. I know Rich and others around here really like this as well, because it puts a focus on goals. This is really nice. This is you could say that everything there is about an agent acting in the world is about its ability to achieve goals. And that says intelligence is the computational bit of that. It doesn't mean it happens in a computer, but it means that the act of computation to achieve the goals is what we call intelligence. So then we can jump into artificial intelligence, and McCarthy says, is the science and engineering of making intelligent machines, especially intelligent computer programs. So then I usually mentally find to replace this with Oh, well then, artificial intelligence is the science and engineering of making machines that are able to do that computational part of achieving goals in the world. Wow, machines that can actually start to figure out how to pursue and achieve goals. Is that cool? Everyone's good with those definitions for now? Okay, awesome. Sort of almost again, like going back to law, it's very much like we're sort of spelling out all of the case law precedent for the kinds of arguments we're going to unpack later. You'll see as we start to talk about reinforcement learning, this kind of like precursor definition of establishing the earlier facts is really important, because if we chose a different definition of intelligence and then started talking about RL, we'd have very different conversations, and they might be, in my opinion, more confusing. So I'm trying to like, let's all come out of this, maybe me as well, understanding reinforcement learning a little bit better, because it's such a really, really beautiful field of science in biology and in computation and machines. So, okay, this is all good. So I'm gonna move forward with this if everyone's okay with it. Okay, good. We're good. I'll just show you. This is actually, if you want to see like achieving goals, this is our pilot from the Cybathlon. We in fall competed in the Bionic Olympics. This is like it's an international rehab technology competition. This is just training in the lab on campus. I have later ones from the actual competition itself. But this is our pilot, Chris. He's someone who has lost his limb above the elbow, and he's working together with his bionic limb to be able to, in this case, concretely achieve goals in the world. Like Chris is racing against time and against all the other parts of this particular challenge, tasks, and considerations, to be able to manipulate objects, to place them in specific areas. I'll just if I can, I'll restart this video of him moving a ring around a hot wire maze, which is a hard task for anyone, let alone someone who's having to pilot a robotic device. And what's neat here is like, we can think about goals. We can think about Chris wanting to move that ring as fast as possible around the wire maze without touching it. If you touch it, it actually lights up all blue, and then you're like, okay, failed the task, you have to drop it. And like moving all of those different objects and pointing them, well, there's clearly goals here. There's multiple machines and human decision makers playing together. The robot arm has some kind of machine learning equipment on it. Chris is clearly a skilled decision-making system. And so like, what is it? What are all those pieces that come together so that someone like Chris can work together with other pieces of technology to be able to achieve those particular goals? What kind of computations need to be put into place? What kind of technology?
Is this the Blink lab in
level 5? It's our lab, yeah.
So we are neighbors. I'm in the level 5. I'm from Smart Network, iSmart.
Okay. So wait, are you over in Vivian's lab then, or are you at the other side of the wall?
Vivian's lab. So
okay.
Like I'm in the device development, so we are neighbors.
Yeah, we are. Device development. Oh, so you're right across the wall from us.
Michelle, yeah, across the wall.
Oh, you're totally on the other side of the wall. Yeah, you're in our virtual reality and augmented reality bay and the student area, and then you like tunnel through the wall, we'd see the CNC machine. And
last month we came to your lab.
Ah, good. Okay, good. Yeah. Yeah, so our lab is all about transforming the science and the art of prosthetic restoration. Yeah. And so we're doing a lot of like very future-looking work, like can we build a competition-grade robotic limb for someone to be able to compete when amounts to the Rehabilitation Olympics, and can we build devices and surgery, like bone anchoring surgeries, to be able to connect people to machines in new ways. Anyway, yeah?
I'm just really curious about how that's working. What kind of connection is going on in the arm, between the arm and the the prosthetic? How is that working? Because is it neural? Is it muscular? I'm so curious how that's working.
Yes, it is. So okay, so it's really cool. I like this example. I'll just put this was sort of just like a segue to the other bit, but I'm happy to dwell on it because it's cool and it came out of our lab. It's timely, and so I'll just show this again. So and maybe I can even pause the videos. Can I do it? Yeah, I can. I have technical skills. Okay, good. So I can pause the videos. So cool. So this is our bed-to-arm platform we built in the lab. And why I think your questions are really like exciting is because in this case the interfaces are varied and many. It's not just a monolithic system. For what Chris is doing here, he has as a sort of one bit, maybe I can't zoom in, but there's in the socket that goes around his digital limb, there are electrodes that are placed in contact with his skin. And those electrodes monitor the electrical signals generated by his muscles. So his brain sends a signal through his nervous system to his muscles. They contract, generate juice. They generate electricity, which can be sensed at the skin. So this is the clinical state of the art, is myoelectric control, taking the signals from the muscles and mapping that to control the arm. What's cool about this though is there's only, like Chris is generating signals with his muscles. Those are being picked up by electrodes. Those are being passed to a piece of machine learning equipment, which interprets those signals. And then allows Chris to control both the flexion extension of his elbow and also the rotation of his wrist. But not the hand. That's what's cool, is that the interface for his hand is in fact a cable that runs, you can just barely see it. I'll just try to point it out, it's hard to see. But there's this cable that sort of runs up here around his shoulder and connects over the other side of that harness. To open and close his hand, he's very gently shrugging his shoulders. It's literally a mechanical cable. There's a wire, a bone cable, that goes, it's attached here, goes around his back, and when he shrugs his back, it goes to what's a linear transducer, essentially like a measurement equipment that opens and closes the hand. So, well, like we worked with, this isn't us just like building a system and giving it to Chris. We've worked with Chris for over a decade, and we're like, this system we co-designed. We gave him this menu of options, like, how would you like to control this joint, this joint? So the answer to your question, that's why I said it's doubly exciting today, is that he was using essentially just like shrugging of his shoulders and his precise body positioning to precisely control his hand. And so he felt that was the most reliable. He was using machine learning mediated muscle signals to control the other joints of his limb. And so similarly, you could imagine, yeah, you might tap, like there's examples I don't have in this talk, but you can actually run wires directly through a titanium shut in the bone, out under the skin, and connect them directly to the nerves of the human body.
Oh, wow.
So you could be connecting to muscles as well. So nerves, muscles, you can pick and choose what are the most functional ways of getting the will or the intent of the person out of their body and delivering that to the machine that's supposed to assist them. Whether it's an artificial limb or an exoskeleton or a powered wheelchair, whatever it is that you might be looking at, or a robot dog, like how do you want to map yourself out in the technology around you? And I think we're seeing a multivariate approach now, and I find that really exciting because it means we're not sort of pigeonholed into just saying, well, I guess we have to sample everything from the brain. All right, where do we put the hole in? Let's go ask Elon. No, like you can actually start to be more precise about, well, what's the best signal to record from the human body to be able to help the person live the life they want to live with the devices they're using to live their life. Now, what's cool is that like, this actually is really on topic for today as well, because when we start to think about a machine that's making decisions in its world, that's learning through trial and error, we have to say, well, how is that machine perceiving its world? What kind of input is going into it that lets it make good decisions? Ditto for this situation, both for Chris, who's getting sensory feedback in different ways from his environment, and for the machine that's supporting it with all its various machine learning technologies. There is actually reinforcement learning technology running on the limb, but we didn't turn it on for the competition because we had other things that we were doing. So, but I was like, well, I was doing a media interview on this after the competition. It was like, oh, was there that continual learning stuff? I was like, well, I don't think so. And our lead engineer was like, actually? No, it was totally running on the limb. We just didn't press the make it do stuff button because it wasn't being used. Anyway, so this limb also has some RL tech on it. Okay, so why did I go through that? Hey, thanks for the question. That was great. So why machine intelligence? Like I talked about intelligence and McCarthy's definition of intelligence. I showed intelligent systems working together to solve what actually is a pretty complex sensory motor learning task. So then we might say why machine intelligence? And I guess this is where I'm going to ask all of you. I realize I didn't make a build on the slide, so you get some of the answers that I think. But you've had lectures as well from the other, like Osmar came in already?
Yes.
Okay, so yeah, why this machine intelligence thing? Tell me what you think. Even if you're not in the class, tell me what you think. Like, why should we pursue something like machine intelligence?
Because sometimes, like if we code a machine, it's not highly specific, and it can have like presets, but user to user, it can be like augmented. So if the machine can specifically learn from the user, like with time, it can regain the ability to be like flexible to use. Yep. Like even exoskeletons, like when the exoskeleton is like delivered to your home, it's like it has presets. But when you work with this exoskeleton, I think like it's becomes more user friendly and
Yeah.
good.
Yeah, we had a great legal debate actually about that exact topic of exoskeletons that I learned how to deploy. Cool, that's great. So then, like other stuff, like what else did you pull out from the previous lectures? Like, why are we all caring about this machine intelligence thing? Or do you? Maybe we should.
Honestly, I agree with the idea that it could be, at least for machine learning, it's going to be very hard for people to be able to be very specific. For example, one doctor to have a lot of information and specific information, and if we're applying this to medicine, whereas with machines, you're able to have like more of a general and a specific kind of like outcome, a something that's more tailored to each individual. So I feel like understanding machines and being able to teach them to do that is I think it's very important.
Cool, you're giving my next AI in medicine lecture. That was fantastic. I love that summary. I'm like, good, this is excellent. Yeah, you should come and do some next. But yeah, that's I like when I think about especially AI for medicine. Those are exactly the kind of points I like to call out, and I think that's right on point. Do you thoughts as well? Anyone else thoughts?
Basically,
Yes, and
copy and paste.
copy and paste. Cool. I've used these. I'm using these slides. I've used variants of these slides for like probably. Kim's like, yeah, I've seen these slides since what 2013. So thanks, Patrick. Yeah, actually, the slides I'm going to be giving later are the ones I gave. I think the first time I did this guest lecture for you, I think in 2013. So I just copied them into a new template. It's
golden oldies.
Well, I think they're useful. So I like going back to this because I think why do people like, and maybe you saw this come out in Osmar's lectures as well, and actually other technology lectures that you've heard that aren't about machine intelligence. Like one reason people I think pursue intelligent thinking systems that are embedded within some kind of like machine footprint is that it gives enhanced control over a really complex world. Like as a civilization, we are trying to like wrangle all the forces of nature that are swirling around us in one way or another, and people appeal to machine intelligence for that. Another is to build that crystal ball that we see in all of our science fiction and mythology, and like even rolling the knuckle bones of sheep to predict the future weather. Like we look to intelligent machines to also give us some sense of anticipation or forecasting power outside of our usual human cognition, and also to build these generalized tools, to build the sort of the universal multi-tool of cognition to solve really hard problems. We've seen all sorts of examples, and I'll go through more in a second of like how people have pursued machine intelligence to control complex systems and extract massive amounts of information, make sense of that information in the world around us. This is my student Gautam Vasan. Now he's a PhD student actually with another faculty member on campus. We did his master's with me, and this is Gautam shaking our modular prosthetic limb in the lab. We had like a state-of-the-art, multi-degree of control bionic limb. This was at the time the most advanced bionic limb on the planet. Very expensive. Also broke a lot. So anyway, maybe by the Chevy, not the Porsche. Anyway, this is Gautam shaking the hand. I like to use this slide and sometimes a video of this to motivate it, like, because I just talk about why machine intelligence. Like, we do want that Swiss Army knife of problem solving, but why then learning? And there's sort of three reasons I think that we also have gone from just thinking about intelligent machines, like someone sitting down being like, okay, tell you what, I'm going to write everything I know down, and I'm going to put it into a machine database, and whenever someone asks the machine a question, it will just look up something that I already told the machine. I mean, those are expert systems have really powerful applications, but I think a lot of the earlier approaches to artificial intelligence were, well, let's just encode everything we know about everything into a machine. Well, so why would we go to learning? One is that in fact, and this is a really nice one, things are really unknown. We know what we want to achieve, but we don't have any idea how to do it. That's the handshake example. The reason I put that handshake there is like, I might know what a really good handshake feels like when I'm going and shaking someone's hand, it's very genuine. I have no idea how to program that in. I have no idea to give a good handshake to Gautam, or to any of you here. I couldn't program that into a machine. I couldn't engineer that in if I wanted to. So I might appeal to learning systems and say, well, yeah, I know where we're starting from. We have this robot arm, we have a person. And I know if the person says, yeah, that was a great handshake, that I have a good outcome. But I don't know how to get there. I can't program that in. Another is a very similar variant to that, which is that, well, I probably could program it. If I spent like the next 30 years, I could work really hard to optimize the best handshake in the world for that person at that time. Problem is that person's now like 30 years older, and the robot's different, and it turns out my solution was bad, and now I have to re-engineer the whole thing in 30 years. Like, there was an engineering approach, though, that we would just throw massive amounts of human labor at connecting those dots. Machine learning is another way to connect the dots. Even if we know what we're hoping to get, and we know how to get there, it might be that the amount of effort to put in would be impossible to leverage, and so we appeal to machine learning for that. And another is one of my favorite ones, which things adapt. Like I said, that robot changed. The person you're shaking hands with has changed. So, we also appeal to machine learning when we're throwing our machines into an environment where the operating conditions might be radically different than when they were built in the factory, or when they were programmed, or when we press start. So I think that's another reason why we do appeal to appeal to machine learning. And this is, I think, especially true in like any of the, like we talked about, the fields of biology, legal fields, we have like any kind of fabrication fields that you might imagine. The bodies of knowledge that we're seeing are starting to be added to incrementally all the time, be it case law or genetic information sampled from species that are used in like protein folding experiments. We're continually sampling and changing the knowledge we have, and we expect systems to adapt to that new context. So, okay, that's the 3 reasons why we build machine learning. And then we're going to get to reinforcement learning. Before I do that, does anyone, any comments, questions for now before we move into the next bit? That's cool. Okay. Feel free to jump in. Like, you can totally interrupt me. It's okay. But like, no, Patrick, hey, what about this? I love that. I'm happy to have tangents. In fact, my meetings are usually very tangential. So, okay. So let's go to so reinforcement learning is one kind of learning approach, and this is an approach I really want to reinforce. That it's not just something for machines. Like the problem setting of reinforcement learning is one that's studied in biology. It's studied in the machine learning literature. Like it's something that it's studied in telecommunications. I mean, this isn't just about machine learning. I heard water, I should have, I guess. It's not about machine learning. It's actually just a thing that you might see happening in the dopamine system of mammals and even bees. The octopamine, I think, in bees. But it's not dopamine, it's octopamine. Anyway, but what the idea is that we have an intelligent agent. We have an agent. And that they are interacting with what we call an environment or the world. And there's this loop of experience. If you want to go back to the 1950s or 1960s, you can look at some stuff from the cyberneticists, and they show these awesome fast loops of agents interacting with world. And it's usually this flow of experience, which is the agent takes actions, and the world then returns to that agent new observations, new state, a change in the world. Now, what's neat about the reinforcement learning problem setting, though, is that there's a special signal that we call out in the state, in the observations flowing to the agent, and that's a special signal called reward. The agent is trying to maximize how much of that signal it collects over time. And this could, like any human analogy, fill in the gaps. Total income that you will make over your entire lifespan. Your grades over the semester of a course. How well you do in Kim's course. Like all of these things you could think of those as a accumulation of signals of reward that you might be trying to maximize if you're that kind of person. Most of us are, one way or another, that kind of person. It just depends what that signal is. But you could go right back to things like safety and like the nutrients flowing into your body, and like that's very much why it ties into biology, like bees foraging in the environment or animals hoping for nutrients. So that's the reinforcement learning loop that we like to look at, is the end agent interacting with the world. So if you remember nothing else from today, like this picture is a great picture to remember because it's very much in contrast to a lot of the other views on machine learning that you might see over the course of this course, or in general when you're like looking at like, well, hey, what about these large language models? What about the chatbots I'm talking to every day to help do like my schoolwork? I hope. Anyway, that this is all about an agent living within the flow of experience, within the moment-by-moment experience. And so that's something special about the reinforcement learning problem setting, is that you have this loop of experience. So yeah, if you remember nothing else from today, let's just celebrate that this approach to learning through trial and error involves an agent interacting with a continuous flow of experience.
What do you consider a reward for a machine? Like how, like you're saying before earlier, like with dopamine for humans and mammals or whatever it may be, or why do machines care if you reward them?
It's a similar answer to the question of why do we care, and I think maybe thank you for that question, because this comes up a lot in the whole, if you want to make certain computing scientists grumpy, say, well, where does reward come from? They'd be like, that's the thing that's being maximized. Anyway, we won't have the debate. I like the question today, though, is really great, because when you think about like an animal's experience of the world, it will somewhere deep in its brain, or shallow in its brain, depending on the organism, but let's say deep in the brain for humans, we got like our basal ganglia and the striatum and things like that. Anyway, it's deep in the brain, there's a body of neurons which are going to be like, oh, hey, there's a prediction error about goodness or badness. There's a lot of debate right now about whether that is actually the right view, but there's a body of neurons deep in the brain, which is like, cool, if good things happen, I'm going to have this like positive prediction error. Oh wow, things are better than they were in this situation, or better than I expected. That's going to project out to all those other bits of the brain, especially the front of the brain and the decision-making bits, the motor control areas of the brain. Like those neurons are going to project out and affect change. they're going to change the connections in the brain so that that organism is more likely to, well, I guess go back to the casino, or to have those salty chips, or to drink the milkshake. Anyway, whatever it is that is like driving it, this is important though. Like, it's create that positive prediction that I did better than I expected, or I did worse than I was expecting, is going to change the way the machine makes decisions. And we'll go through this for the rest of the day. But what's neat is that, well, but that has to come from somewhere. And so for the organism, like, well, is there a taste bud? Like, is it that the receptors in the tongue of the animal are now mapped to those deep brain neurons? Does it go to another part of the brain? There's a filtering process that takes the raw sensory motor experience, whatever it is. So it might be the vision system, it might be all the other sensory motor apparatus of that organism. And somehow, at some point, somewhere deep in that whole milieu, turns those sensory motor signals into goodness and badness. Because that's what that central system is saying, oh, well, this is way better than I expected. Well, there's a goodness or badness in there that is in fact really important, or this is like homeostasis, whatever it is. There's a mapping process. And so the same thing is true for machines. Like, you have the various sensory motor aspects of their environment, and deep inside the machine, we'll actually see the deep inside the machine a bit later, but it's like, it has to say, am I doing better or worse than I was predicting I was going to do? So at some point, there's a translation that happens, and often that's translation done by us as designers. But both the animal and the machine are going to change their behavior based on whether they're doing better or worse than they were expected to be doing in this situation according to some signal. And there's a mapping that takes the world and turns it into that goodness or badness. So if you're still on me, you're like, no, machines still can't like goodness or badness. So like, we have part of our brain which is going to be saying, you know, like, I'm getting protein and hydration, and I got sleep, and I feel safe right now, and mapping that to like, that's good stimulus. Similar in a machine, it might be, oh wow, like, I'm putting out widgets, I'm making paper clips faster than I expected. Cool, like, the paper clip production rate could very readily be mapped to good, like the number of units produced per second, or the amount of like tokens that you collect on a game board, or the points you get in a game like checkers or chess. We'll go through examples actually of like reward. This is a great precursor to the next couple slides. Yeah, you're like setting everything up today. This is amazing. But that's like, so I think that's really cool, is that there's this nice sort of like similarity there with the biological and the machine process, which is like, well, all we have is signals. We have lots of different signals about the world, about ourselves, and somehow that gets turned into goodness or badness. And in animals and machines, there is actually something that turns the world and the environment and the self into a signal which is considered goodness or badness. It's that signal of reward. So yeah.
So it's the idea that we've like kind of like practiced the computers or primed the machines to be able to be like, if, for example, like you said, if they process it at a certain speed, it's like good, repeat.
Yeah.
It's okay.
Yeah.
Because I was gonna say, like, there's at least to me, there's a huge difference between humans and machines. And to us, we're like emotional beings and things like that. And I know Dr. Solas was like saying earlier that, or before we had a conversation about how like machines, if they do decide that they can, something rewards them, then they'll be able to start achieving things. But in my head, like, our reward's a lot different than their reward. They don't have the emotional factor, which I feel like is huge.
Yeah.
At least.
And it's neat, because like, you could say like, well, I mean, their reward is going to be way different than our reward. And the way that their environment and themselves are mapped to their reward is totally going to be different than ours too. But the way that they handle the changes in that reward is in fact very similar. And by design, like the reinforcement learning literature especially, has like, it's very closely fed back and forth with the neuroscience literature. So the processes are very, very similar. And they admit things like emotion and models and like, what if you had like, let's take the mind's eye, we're getting much farther in the slides, but like, let's actually think outside the slides. Let's imagine that the machine does have a very detailed model of the world in itself, that it can like compare its current existence against. Well, that's kind of like a little self. Let's not call it conscious, that's getting way too far. But let's imagine it has a model of itself. And now it makes a prediction that its model of itself is going to be getting less reward in the future. Like, there's a sadness there that you might say that is a signal about the future change of its interpretation of itself that has an output signal, which could be chained back into its decision making, which might be akin to sadness. Is it the same? Well, probably not. But it's neat if you sort of think about its ability, and machines do have the ability to build models of themselves and their own operation and their interactions with the world, you might say that, oh, you get signals that are akin to emotions and have a similar function in machines as well. It's gonna look different, but the processes might not be as different as we originally think. Now, is their sad our sad? I don't know. Is mine green apple, your green apple? Who knows? What's it like to be a bat? Nagel has no idea. So we get to all this, like all the philosophy and the epistemology literature of the centuries past, and we still won't come to an answer there. But we can start to say, oh, these processes are starting to look really similar, even if what the actual suchness of the signals are different. The way they chain together might be similar. It's a cool question. I'll keep going if that's okay, just to raise through, like we can skip all sorts of bits of my talk. I really just want to talk about RL with you all today, because that's important and I think we're doing that. So anyway, RL's approach to all sorts of stuff. We talked about natural, biological, and artificial and optical control. So I'm just going to jump right into some RL successes. I like the highlights role, also because I get to talk about other people's cool work and not my own. There's a level of psychological safety there, being like, well, this is what someone else did. You can judge them. But I think a lot of the really large successes in reinforcement learning were first most prominent in games like Go and poker and chess and checkers and shogi, and recently games that are much more advanced like Diplomacy and Stratego and games like Scotland Yard, games where you might not know the full state of the board or your opponent might be hidden and you have to make decisions about it, or you're working in teams. Like we've seen like matches with Lisa Dahl, the AlphaGo matches, where AlphaGo was able to defeat a world champion in the very complex game of Go. Our very own Michael Bowling and the team here in the computational poker group showed that deep learning systems, deep stack there, can actually play unexploitable no-limit Texas Hold'em poker, like to unexploitable levels. You can't say optimal because there's a lot of randomness involved, but that's like playing poker. That's like it is a very challenging thing to do. Checkers, shogi, diplomacy involves like making alliances with other nations and like coming up with strategies. That is also something machines are playing. Scotland Yard is there's a team of investigators that are trying to catch a supervillain in downtown London. A supervillain only appears every couple of turns, and machines are able to play the role of either the supervillain or the team of investigators trying to move through the city to find. So like these are board, like imagine these are like in the board game or games of like card game of skill kind of things. And reinforcement learning has shown massive successes in playing optimally or perfectly in many of these different situations. So that's already cool. What about video games? Because of course everyone likes video games as well. I like video games. And we've also seen similar successes in reinforcement learning playing video games. Actually, a lot of our U of A graduates are on the team that are working on Gran Turismo Sophie. This is the racing game from Sony AI and Sony. And Gran Turismo, they showed that a reinforcement learning agent could learn to race at superhuman levels in the world's best racing driving simulator. I mean, I'm no horse in the game there. I think it is the most like realistic racing simulator on the planet. And what's cool about that is through processes of reward, whatever the reward, whatever that goodness or badness signal is, the system was able to learn not only to do really impressive and sophisticated driving maneuvers, but also learn to be able to follow the rules and conventions of racing, to not smash into other cars, to not do inappropriate things on the race course. It was able to learn the human conventions of racing. Similarly for Minecraft, we see that AI systems can actually play Minecraft, like create diamond axes or whatever. My son plays Minecraft. I do not. I think I should. Atari, Capture the Flag, StarCraft 2, Dota 2. Like we see machines that are playing at like professional level, like the StarCraft, the AlphaStar work. Like you see like an AI system servoing Zerg units or Protoss units in a StarCraft 2 game. It's very impressive to watch it like digital mind's eye playing an entire map at the same time. So that's the video games. It's all not just fun in games. There's lots of practical stuff too. This very same mechanisms with small modifications that we're doing those other impressive things in physical or video games can control and stabilize plasma at the heart of a tokamak reactor that's hotter than the heart of the sun. Like thousands of times a second. We have a reinforcement learning system. This was done by colleagues at DeepMind in a tokamak reactor in Europe, but could actually use reinforcement learning 1,000 times a second to stabilize the magnetic field in a fusion reactor so they could change the shape of the plasma, break it into multiple droplet shapes, and to stabilize and control the actual fusion. So this is real world, real decision making. Of course, the don't explode the tokamak reactor is a great reward signal if you're looking at reward signals. But it had other reward signals that were more fine-grained. But it's like, it has this rich sensory motor space. It has the ability to change all of the performance of the magnets to stabilize fusion. So that's like another application, but it's like the technology underneath. Again, the way it engages with its world is different, but the underlying technology is the same. There's also like looking at simulating matter at the quantum scale, robotics. I'm sure some of you saw this work from OpenAI where like a robot hand is able to solve a Rubik's Cube. So it just sits there like learning from scratch how to actually solve a Rubik's Cube. Like everyone loves robotics, so I have to show at least some robot videos. And this one is, yeah, there's a machine that's like, figuring out over time through trial and error learning, through processes of reinforcement learning, how to make a Rubik's Cube into its solved variant of itself.
Does it actually solve it?
Yeah. Oh yeah. And they show like you can put like stuffed animals and stuff in there. You can mess with it, and it still manages to get through the process of solving. I mean, it's slower than a like I've seen those like professional human Rubik's Cube like solvers. Like that's ridiculous. They're like blindfolded, like doing 4 at the same time while juggling. I'm like, how? So similarly, like there's been great examples in telecommunications. Our very own Marlos Machado, who's now faculty in computing science here, he worked with the Google Brain team and the Loon team to help lead out some of this work, which was looking at autonomous balloons over sub-Saharan Africa. So to be able to deliver internet to locations on the planet that don't usually have really reliable telecommunication access, they put a autonomous fleet of balloons into the stratosphere, like high altitude balloons. They're independent. They can do whatever they want. They can go, and what they found is that they actually were able to, through reinforcement learning, be able to configure themselves into this like beautiful mesh network, be able to change their altitudes to continue serving internet, and would even do things like they're like, why? Marlos gives great talks. You should go like look up one of his talks on YouTube. But like he talks about how there was this like weird phenomena they observed in the altitudes of the balloons at nighttime and daytime. And what it turned out the balloons were doing is they were learning to, based on the currents of air that flow at nighttime and daytime, they were learning to take naps over nighttime when their solar panels were not functioning at different altitudes so they could coast and remain stable and then like change altitudes later on when their power systems were operating differently. Like, again, a system that's able to use signals of reward to perform and affect really complex behavior, like coordinate a fleet of balloons in the stratosphere to serve internet. There's other systems as well, like Sanctuary has put a lot of work on reinforcement learning. I might dwell on it, but they're fully humanoid robots. There's a number of others too that could go everywhere, from like certain companies that are like having people remote controlling their robots from backstage to actual reinforcement learning in robots. And like we could go on, like there's all sorts of cool stuff. There is work in like climate on data center cooling, RL, to be able to save like 20 to 60% of the energy waste of data centers through optimizing the cooling process using reinforcement learning. Water treatment, our very own Martha and Adam White here at U of A have a company called RL Core Technologies, and they're looking at reinforcement learning to figure out how to more efficiently provide water treatment, especially water treatment in remote locations, like indigenous communities in the north and other places in the world where they might not have large-scale like expertise and people that are able to manage their water treatment. So like automated water treatment when you flush your filters and things like that. Economics, AI, like reinforcement learning systems can learn the fundamentals of supply and demand and arbitrage. They can learn how to actually perform acts of bartering and resources and like supply and build supply and demand curves. There's taxation design, governance approaches where you can see machine systems learning to build taxation approaches that humans would actually vote for. Video compression, throw the same game. This is literally the cool bit of the video compression. You can literally throw the same algorithm that's able to solve chess and checkers and shogi, and you throw it at YouTube data and say, you know what, I want your reward signal is how much compression you can make in this video stream without losing any quality, and it will save like 10% or more of the bit rate of all YouTube videos on the planet. So just take mu0, again, literally the same algorithm that's like, yep, I can play chess and shogi, and you say your game now is video compression, and it nails it, and you save 10% of the bandwidth on the entire planet for YouTube. That's like, there's good human level coding, like through RL you can have systems that learn to do like human level competitive coding, self-driving vehicles. There's, anyway, we can go on, like visual asset creation, expert diagnosis. There's also, I don't have it on here, there's also legal. There's like, Randy Gamble here on campus has worked on legal reasoning and actually has AI systems that can pass the bar exam, the Japanese bar exam, and like able to think about, like, through process of learning to be able to do, like, advanced legal reasoning, so. Okay, cool. Those are, like, that's my, like, best of hits collection, or I mean, there's lots more even by this day, but that's like does that give you a good sense, though, of, like, apropos to our conversation earlier, like, there's signals of goodness and badness, but across all of those domains, like, the reward signals, that sensory motor loop of experience. If you're a high altitude stratospheric balloon versus a nuclear reactor versus a Minecraft agent, like, your sensory motor experience is radically different. Even the timing of it is different, but it's an agent living within a flow of experience, making choices to try to maximize a signal of reward, whether it's not blow up the tokamak reactor, let's keep the fusion stable, or trading the most bananas with the people who have apples in my simulated bartering game versus keep the self-driving car on the road. Those are all different reward signals, they're all different sensory motor spaces, but they all follow that same process of experiential learning and experiential, like, embedding within a flow of time. Questions, comments now before we move on to the next bit? I think I'm still on time. Probably still on time.
Yep,
Okay. It goes to 3:20, right?
3:20.
Oh, perfect. Okay. All right. Do we want to go into how it works then? Like how it works? It's really simple. I mean, I don't have any math, but we're going to start with prediction learning. So I'll start. These are actually, I'm sort of paraphrasing slides that I know Rich liked to use from back when he taught with transparencies. So, like, that tells you how old that was. Does anyone still go to any lectures where they use transparencies? No? Okay, I think you probably have, like, none of your classrooms have transparencies?
What's traffic?
Okay, this shows all of them. It's where you have, like, an actual overhead, you have a projector
Yes,
with, like, the light comes up, and you put a clear slide that you've written on, and it goes up to a little box, and it bounces it out to this,
Projector, yeah.
right? It's like the one that's, like, you actually have a projector, but it, like, shines it up through the transparent sheet that you put
write
on.
the.
You totally write on it, and then you'll come, like, professionals will come to the class, or, like, instructors, even in my high school, people would come to class, and they, like, stack their, like, transparencies, and they have to make sure they get them in the right order, or, yeah. You must have taught with these.
I have experienced that.
Yeah. Even I've taught with them.
Yeah, in 2013 when I was undergrad, I have seen those, like, they write it in a transparent paper and put it on projector. Very old school though.
Yeah, exactly. Anyway, so the original version of this, Rich Sutton had some of this on some of his original slides. So I like it, so I use it. So imagine you're like a learning system, and you want to make predictions about the world. I said that reinforcement learning was sort of foundationally tied to the idea that you're making predictions about things like goodness or badness, and then you're seeing how well you're doing. So let's agree that the whole system is sort of, like, built upon a process of prediction. That's a great standpoint to start from. So imagine your system is Monday, and you're like, gee, I wonder how much, I'm an intelligence system, I want to predict how much rain or how much snow is going to fall on Tuesday. So that's what we call a one-step prediction. So we might be making predictions about just what's going to happen next, on the next time tick, whatever that is. For that tokamak reactor, your time ticks are 1,000 times a second. But for, like, a system like this, maybe it's what happens every day. So, like, you're an intelligence system, you might say your prediction is 7 millimeters of rain that falls, and then, like, 10 millimeters that falls on Wednesday based on what you know about Tuesday, right? And you might even say, okay, given what I know about Monday and Tuesday, I'm going to make a prediction about how much rain is actually going to fall on Wednesday. Okay? I think this is probably, we all make predictions like this. This is a very straightforward style of prediction, and a lot of sort of supervised learning systems make predictions like this. There's something special, though, about the technology that underpins reinforcement learning, especially in machines, but also in animals, which says that, like, it's making a temporally extended prediction. The system itself is not just predicting what's going to happen on the next step, but it's sort of making an estimate of that expected future reward. How many cookies will I get from now until next week? How much money will I make by the end of the year so I can go on the vacation? Like, it's thinking about a temporally extended collection of rewards or signals that are coming in. Here I'm talking about rainfall, but you can imagine that this could be a signal of reward or any other signal of interest. And it might say, okay, given what I know Monday, I predict that, like, 32 millimeters of rain are going to fall across the entire week. Now, if you're like me, you might say, well, I want to go to Folk Fest. I want to go listen to some music. Do I really care about Tuesday, Wednesday? Nah, I'm going to be inside at the university or something like that. But on Thursday, Friday evenings, I care a little bit because I want to be on the hill listening to music. And Saturday, Sunday, all day, I want to be there with my kid. It's going to be awesome. So now I might care about a certain part of the future more than I care about other parts of the future. There might be a weighting to how I sum up those signals in the future. In this case, let's say signals of rainfall. I might really be caring about predicting or estimating how much rain is going to fall over some distribution over like my Folk Fest days. Okay, so that's prediction. Like, I just want to go back to the previous day. Like, these are important if you want to think about and talk to people who pursue reinforcement learning and other machine learning technologies. Often we're thinking about one-step predictions, but for that system that again is trying to stabilize a reactor, trying to do a great job of the game of Go, it's important to think about these temporally extended predictions. These systems are trying to figure out, they're trying to predict, they're trying to learn how much reward they might get over some window into the future, assuming they care about the future according to some window. Is that cool? Again, no math. We can do math. It's really simple, but this is like the core of everything. Okay, cool. All right, so that was prediction learning in a nutshell. Okay, good. Now you're all, actually, here's your AI degrees, you can all do. No, it's control learning. Okay, so you have predictions. What do you do with them? So this is like, if I'm a system that is trying to act so as to maximize my long-term expected reward, the reward I get, like how much money I get until the end of the year. Well, that means I should in some way be using my predictions to change my own behavior. Like what I've learned about the world, what I know about the world, should influence how I act in that world. I mean, I hope that's true for all of us. That we're like, what we predict about the future changes how we act in the world. I hope so. Okay, so imagine you're an intelligent system now, and you're in this this isn't even like this is not like racing in Gran Turismo Sophie. This is just a very simple grid world environment, a little branching decision process, a Markov chain. A very simple Markov decision process, actually. So, okay, you're an agent, and you hit location 1, and you're like, well, okay, I have a choice. I can go to location 2, I should go to location 3. Where would you go?
So I'm in location 1, right?
Yeah, you're in location 1. Where would you go? You're the agent.
Anywhere, I don't know.
Right? You have no information.
Yeah.
Okay, so what would you want to make a decision about which one of the 2 locations you go to?
So personal interests, like if I'm attracted to that place.
Ah, good. Okay, good. So you bring valence on it. You're saying goodness and badness. Excellent.
Yeah.
Okay. Good. So you like one way you might do it is to actually use those predictions, those learned values, those learned expectations you have. Like if you have an estimate of location, like location 2, and you estimate, oh, if I go there, let's just use money and assume you like having money. I don't necessarily mean you all. I'm not trying to say that you all do. I don't want to assume anything about your cognition. But let's just take the perspective that the agent, that more money is better for this particular agent. So now we look at this and it's like, oh, its estimate of location 2 is $55. And its estimate of location 3 is negative $10. They're going to lose $10 going there. What would you do now?
Definitely location 2.
Right? Like, that's good and that one's bad. So she's like, that's cool. Okay, awesome. Now, let's say you go there, and then you're like, oh, wow, I actually got $60 from going there. Like, you guessed 55, and now you got 60. What would you do about your estimate of that location?
I'll be happy about my estimation capacity.
Yeah, and would you change your estimate?
Yeah, like
How much?
like I will increase the precision by +5 because I was
Sure, that's a great, yeah, right? A totally reasonable choice. Like, okay, I guessed it was 55, I got 60. One reasonable thing, this is if you had a step size of 1, in fact, that's like that. You would change your prediction to be the new thing you observed.
Yes.
Now, if you were uncertain about your world, you might be like, oh, you know, I don't really want to update it all the way to 60, because what if next time this is just, what if it was rolling a dice, like 20-sided die, or 2d6, or whatever it is. So maybe I'd update it to 56 or 57.
Yeah.
Right? Like you might choose how you update your learned predictions. But this goes back to like you have a process that updates your predictions about this state and future states, and now you're applying that to how you're making decisions. Okay, cool. So that's one way that you might use those learned estimates to begin to update how you act in the world. Right? It's pretty cool. So another way is what we call using a policy. So this is different. So what we just saw was you actually had some kind of model of the world. Like when you were looking at that, you're like, yeah, I'm using those values I've learned. That's my like, you know, I've got this little fake version of the world in my mind. And that little fake version of the world had a 55 and a negative 10 in it. I use that to make decisions. It's my expectations of the future. You might also make decisions based on the present. So this is another way that you might start to think about making a decision. So now like, imagine you just know, like imagine there's not just location 2 or 3, there's like a billion different next locations. Going through all of those locations and figuring out the estimated values for each of them, that might be either time consuming or computationally intractable or just really boring, you don't want to do it. So you might just make a decision based on where you are right now. This is very much like knee-jerk reaction style in the animal learning literature. Like I'm in location 1, and based on everything I know about the world and how I've been born into the world and all the things that have been programmed into my brain, 80% of the time I'm going to go location 2, and 20% of the time I'm going to go location 3. So, like, let's imagine that exact same thing, like the same calculation you just did, except now you just rolled the D100 and you got like, you know, under 80. Cool, you're going to location 2. Now you still got that $60. Now instead of updating the values, you might update your policy. You might use that thing like, that's a difference. Like, you got reward, sure. But if you got 55 when you went to the place that you expected to be worth 55, you might not change anything at all. But if there's a difference, that temporal difference, error, this is again going back to the dopamine cells, like the dopamine neurons are projecting out what we could say is that difference, a version of that difference. Then you might change your probabilities of acting in location 1. You might say, you know what, next time I get to this location, I'm at 85% versus 15%. And so now in this case, the kind of reward you're getting is changing the way you act in a situation, not the way you value other situations. These are two very different ways that we might think about learning. Both of those ways are thought to be play different ways in biological reinforcement learning systems. And similarly, we see some of those examples I was showing you. In fact, in the AlphaGo example, there are systems that are learning policies and there are systems that are learning values. There's a value network and a policy network, actually. And so you might see both of these kinds of learning deployed in a single machine. Okay, demo time. Yeah, we got time for demos. Let's do it. I actually have this. Okay, demo time. There's another one here. I'll just show you the demo we're not doing. This is in. Did anyone use Unity, the video game environment? No? Okay. I'll just start with this before we go to the other demo. But if you want these slides, I think they're on my website. They should be on my website. Just look for the RO without the math talk. I think I last gave it probably in fall of 2024 to the Student Developer Conference. But you can just download Unity. You get the student version of Unity. It's free. It's a video game development language and platform, and it uses C# as the language. There's a little toolkit called ML Agents. You can install that, and then you just play with it. And the tutorials are really good. Like this one, you get a host of little boxes, and each has a ball on its head, and it's trying to bounce the ball on top of its head. You see, like at the end, they're all just randomly wiggling around, and the balls are falling off everywhere. And by the end of 30 seconds of learning, they're sitting there and they're perfectly balancing the ball on top of their little box heads. And there's other examples. There's like walking around in mazes and things. So if you want to play with reinforcement learning, there's lots of ways you can download. Like there's, I think, the RL Gym. There's like all these different. Let's Google how to play with reinforcement learning. But this one's really fun because then you start making your own game environments. And I like building game environments. But that was not the one I was showing you. We're gonna go to this one and see if I can actually bring this up here. Just gonna pop that out here and then minimize this one. Okay, cool. I'm gonna minimize everything because I'm on camera, and I want a confidential conversation with my students, telling them how awesome they are. Okay, there we go. Okay, good. So this is freely available for Prabhati. It's an online reinforcement learning sort of environment. So if you want to play with it, just click the link in the slide. Joe won't take you to. It's not going to rickroll you, I promise. So like what you can do is like here we have a little agent. This little yellow dot is the agent. So sorry, I can't highlight it properly. I'm not doing anything. Anyway, you can see this little yellow dot here. That's the agent. This is the grid world. And if you look at the bottom here, this is a really simple view of it. This is the reward, -1, -1, -1, and over here somewhere is a 1. Okay? So if we just toggle, let's go slow, and toggle TV learning, we're going to start to see the agent exploring its world. So this is the little agent exploring its world, and you can see the arrows are showing its policy. The arrows are showing its preference for moving in one way or another in this little grid world. And you can see the green or the red shows its valuations, like those values in those two states that we were learning about before. This is actually showing the value that it has learned for each of those states. And so it's, again, running around the world. It's got all sorts of parameters, but in this case, it was trying to explore to find the fastest route, because I think it gets a small negative penalty on every step that it acts. So it's trying to get from that first bit to the end bit there as fast as possible. When it gets to that our reward equals 1 goal, it's going to teleport back to the beginning. So that you can see it learned really well. So now if I toggle T learning, what should we do? Should we can I make a wall there? Can I do a wall? Let's find out. No, I can't. How do I make a wall? I should remember this before I did this. All right. Oh, reward. Let's do this instead. So I can do this easily. I can't remember how to make a wall. I can never do this. So like, what if we were to make the reward -1? What do you think's gonna happen? Like, you can see its path here is to go here the straightforward way. That's the fastest way to go. It's not gonna go through these negative reward spots. That'd be silly. Like, who wants to eat that -1 reward? So what do you think's gonna happen if we were to make this reward negative now and continue learning?
It's gonna find another route.
Yeah, right? Where do you think it's gonna go?
All the way correct.
On the top, it'll just go on the top and then down?
Keep going straight.
Oh, but there's an arrow going down if it crosses that way. Are the arrows going down how, like, the direction that it has to go?
It doesn't have to go, but it's the direction it thinks is best.
Oh,
So when it gets that environment, like, it's gonna have to make, this is cool though, right? It's gonna have to make a decision. Do I like deterministically, precisely follow the arrow that I've learned before? If it does, it's stuck in this wall. It's gonna permanently go through, like, this would be bad, right? Like if you were to say, oh no, I have to follow my arrows from the past. So probably it's gonna randomly try things out, right? Like, I like the ice cream store. Before we do this, I'm gonna do a slight tangent. Imagine the ice cream. I know, maybe some of you don't eat ice cream. Imagine I eat ice cream. I like ice cream. And I go to the ice cream store. I'm like, okay, there's a bunch of tubs in front of me. I can't see what's in them. So I'm like, oh, okay. I go in. Maybe I try. I say, I'd like one of this, please. I'd like to try the tub second from the left. Oh, it's mint chocolate chip. I like mint chocolate chip ice cream. This is fantastic. So I get some of that ice cream. Next time I come in the store, I mean, there's one thing I do, which is like, well, I have no information about all the others, and I clearly have information about this one. I'm just gonna go back to that one. Like, that's just following the arrow over and over and over again, right? But I mean, I might be like, well, there might be a better one over there. Like, what if that's like lemon sorbet? I really like lemon. I like lemon sorbet. So maybe like, I'll try. Maybe there's a better one. So I might go in and, you know, every time I go in, I try the best one that I've ever tried before. But then I might like take a risk one day. I'm like, yeah, no, today I'm gonna try a random tub I haven't tried before. I'm like, oh, it's earwax, awful. No, never do that. Never do that, right? So like, I might be trying to like balance how I explore the world and how I exploit what I already know. And this is the explore exploit trade-off from reinforced learning. When we see agents and their design, that usually what you see is that they're interacting with an unknown environment. We have to encourage them to explore that environment, just like we would do, and we have to also make them able to follow what they know is the best way to engage with that environment. So let's run it, let's talk about T-learning, see what happens. It's like, whoa, that's bad, that's bad, that's bad, that's bad, and like, as you all called, like, very shortly afterwards, can I tick off? Yeah, I can change that. Yeah, whatever. Perfect. So now, like, it very quickly built up an estimate of that square being bad, and then changed its route. But look, it's sometimes going down the bottom, and like, what just happened? Huh? So that's that exploration in progress. It was occasionally taking a different route, following the policy of that route, and seeing what would happen. Now, you might be noticing something else sort of sneaky is happening here, is that sometimes more arrows are changing than just the ones it touches. There might be other background updates going on based on its learned model. It might be actually doing what we call planning. Okay, so that's one cool one. I'm just going to check the time. Do you have any questions about that? Do you want me to try something on this particular grid before I move on to another example? Anyone? Like, what if you make this one negative? That was bad. Let's do that. Let's make that one. Let's make it minus 2.4. I know that's awful, but let's do it anyway. Oh yeah, 14, right? I wonder how. Let's go really fast and see what happens. Does it ever manage to figure out a new path to the goal? Let's see. Okay, now we go normal. Did you have to get there? Oh yeah, it's getting the goal. Okay, cool. So eventually, like this, again, reward is all relative. If you're like in Alberta and you're like, oh wow, it's been minus 30 for 2 weeks, and suddenly it's minus 10, you're like, this is the best thing ever! And you invite a visitor in for faculty interviews, and it's like, I just came from like the tropics, and your minus 10 is the worst. Like, so it is very much like the way that systems and agents treat reward is very relative. Those valuations are all relative. And it turns out that you can move around their scale and their set points, and the learning process relatively stays the same under some certain assumptions. So at this point, like eventually the system will start to learn what the right moves are in the world. And there might be a world where it's better to run around the world taking a -1 penalty on every time, or a -0.1 penalty on every time step, than actually getting to the goal. So, okay, so that's one example. I'm gonna put this back to like positive now. We need some positive. Oh, let's do this. I'm just do this instead. And see if that changes. Whoa! Bananas! So that's bananas, right? Now let's go slow. And now notice something else that's really bad. What's happening?
It's going back and forth.
Totally, right? So it rarely ever goes to the goal. It only goes to the goal by random chance. That random explore action, it pops up, hits the goal, and gets teleported back. Otherwise, it's just going to sit there. Like all it has, it's going to sit there and go back and forth, try and get back and forth into that state with a super high reward. Now, this actually ties really nicely into things like addictions research and how the brain, like the bushiness of the dendrites and the dopamine system change during addiction and withdrawal and things like that. Like there's really neat biological consequences of exactly what we're seeing here. But those high spikes of reward can in some cases completely change an agent's behavior, even when the task itself is very clear. So does that sort of make reward functions clear, like how they sort of play out? I'll do one more demo. Let's do water world or puck world? Let's do puck world, DQN. So this is another cool one. Okay, the agent's trying to get to the green dot. If I remember this one correctly, it's trying to get to the green dot while staying away from being anywhere in that red envelope. So it's trying to go towards that little green dot. So it's not doing a particularly good job right now, is it? No, it's not. So let's speed up a bit. Oh, it seems like it's doing a bit better, right? So this is using deep neural networks. So this is using DQN, I think. Let me just double check. Yeah, deep Q learning. So the first one we're using was just using a linear learning machine. This one's actually using a deeper neural network, which is just another way of representing and like all of the translation act of going from the sensory motor space to the actions. And if we go fast again, okay, and now let's go slow. We actually see the agent doing a better job, right? It's like, does it go in? Does it run in? No, it doesn't. But it's like it's trying to get to that and avoid. Like, over the course of this short little amount of time we've been learning, we see this like nematode. It's like a very straightforward, simple organism, which is doing what nematodes do, right? How do I steer? Great book by Max Bennett, by the way, A Brief History of Intelligence. If you want to dive into like the foundations of how human intelligence came about, Max Bennett's done a great job of writing this like a very engaging narrative that goes right from like single cell organisms and nematodes right up to like primates and humans and how we make decisions. It's a really cool book. But nematode, this is very much like our nematode level intelligence. And if we load a pre-trained agent, let's just load the pre-trained agent. I think it just did, yeah. This is about as good as it's going to get. Like it's hovering away, trying not to get too close to that red envelope, and sort of ducks out of the way. Like this is kind of like you see very simple like multicellular organisms exhibiting the same kind of behavior if you look at them in a petri dish, right? And we just have a machine that just learned that from pure reward, while we were watching it. The last one I'll do is water world as well. This is another similar kind of one where I think it's confusing in that it gets reward for picking up red dots now and not green dots. Yeah, I think it's trying to get the red dots, not the green dots. I don't apologize for it because I didn't make this. Karpathy did. That's cool. It's cool. Okay, let's go super fast, and then we'll see. Then we'll go normal again. Now let's have a look. Again, going back to our sort of prebiotic soup and organisms trying to catch other things in a swimmy little tide pool. And the agents, when does it duck off? Like it's learned something like, if I hang out by the wall, I don't get hit by the things I don't want to get hit by. And then it's like, oh, when do I duck out to grab things? Come on, little agent. Let's go fast again. Okay, I want to see what a pre-trained agent looks like. Okay, load the pre-trained agent, go. Oh, hey, here's the exploration thing too. We've actually, oh wow, so pre-trained agent, at the end of learning, here's what it's doing. Like it's elegantly dodging those little green dots and trying to forage for all the red dots. Like it actually has, and you can see its state space. So its state space is like that little like LiDAR plot around it. You can see when it's detecting red and green circles on those rays that are projecting out from its body. So that's important. Like we're talking about what's the sensory motor space of the agent and like what's being mapped to reward. Well, in this case, like the being hit by the red or the green or not doing anything is being mapped to those signals of goodness or badness. That's how you sort of map the sensory motor environment of a machine into its perception of goodness or badness. Cool, huh? Anyway, if you want to play with this, you can do like, I take great joy in playing with this. And you can like jam up the exploration rate and see what happens, and that just makes like totally random calls on almost everything. You can go down and make it perfect, and then it'll just be like flawless, and going back and going, oh, I guess that wasn't flawless. Well, maybe there's momentum. Cool, huh? Okay. Those are the demos. Again, this is just a very straightforward. There's lots of cool demos you can play with, but that's one of them. And now where'd my talk go? Demo time. Okay, we're out of time, so there, I showed you this one as well. If you want to go play with it, you can use RL. It's awesome. And yeah, it's time for discussion. That's so that's more or less, yeah, RL's great. Oh, but I guess, okay, let me just go around and say, just to, like, do you feel like right now, if someone's like, oh, hey, I was hearing this reinforcement thing's pretty cool, like, do you feel like you could just be like sitting at a party or having coffee with a friend and actually like be able to talk a little bit about RL, or even just like feel like you could participate in the conversation? Kind of? Yeah?
Yeah.
Yeah? Nah, not really.
Kinda.
Kind of, maybe?
Maybe it depends how far we go with it.
Sure, right? Like, okay, show me the TD learning update. You're like, no, Gibson, I'm not doing that. But like, to I guess, so simply like to talk about, oh, hey, yeah, like that loop of experience, or what it might mean to learn from reward, or like what different, like, what if we rewarded to do this kind of thing? What do you think it would do? Like, do you feel like you could have those kind of conversations? Okay, cool. You're still like, no.
A little bit.
I'm gonna make an AI lawyer. It's gonna be awesome. Cool. Okay. Any questions then? Like, given that, like, I hope was it okay? I guess the other question is like, was this valuable, or did I just waste your time for an hour?
I definitely do think it's valuable.
Okay. So like, okay.
So can you relate it to DeepSeek? And
Yeah.
Yeah. Yes.
So, like, happily, without again making any comments at all about the technology, what's good and bad about it, I'm just gonna say, like, going back to like, well, how might you apply this to something like a large chatbot? You're trying to build a chatbot, you're trying to make it efficient, and you want it to be able to exhibit properties of intelligence. Like, this is, I mean, for DeepSeek in particular, DeepSeek's R1 model and R10, like the models that were making a splash lately, what they were trying to do is to get it to be able to demonstrate chain of thought reasoning. Like, you have a chatbot and you're saying, hey chatbot, you know what I want? I want you to solve this problem. I also want you to show me your thinking. I want you to show your homework. Like, go in there, show me if you're solving a problem, what you were doing when you were thinking it through. Like, to try to build in reasoning into a chatbot, which you might say is just regurgitating tokens that it predicts about the world. Like, going back to that one-step prediction, like the rainfall example we saw at the beginning, the early large language models were doing just that. They're like, here's all of the tokens I've seen before. Here's all the rainfall I saw last week and what the state was. Here's what I think about the next day. Here's what I think about the next token, the next piece of language. And then that gets bolted back on and makes another one-step prediction. Usually I do an improv game when we try to do LLMs. I'm like, cool, I'm gonna ask you questions. You have to do a one-word story, and you go around the table, and we all, maybe if there's time we can do it. But it's a fun improv game where you go around the table and you ask everyone to answer a question, but everyone can only contribute one word and they have to go in sequence. So that's a large step from saying I want a machine that's able to have a train of reasoning or a chain of thought. Like, I'd say one-step prediction of a token to being able to try to do what we might consider reasoning is a big gap. And so in that case, the approach was, well, if we were to have all of these benchmark tasks that have reward in them and that necessitate chain of thought or reasoning, or we think they do, can we just like have a policy which selects between all the responses? That's the policy we saw. Remember, like, you're in a state, you have to choose which way to go. Can we build a policy that would just start to, through process of trial and error learning, start to get pushed towards chain of thought reasoning just by giving it how well it does on the task and a bit of an extra little bit of reward as to whether or not it showed its homework. Like, that's literally the reward function to my understanding in the DeepSeek work. And that's like, this is cool, is that you just give it a benchmark of task, you say you're getting reward for it, and you can start to see a learning machine exhibit something like reasoning. Whether it is reasoning or not, we can debate that for hours, and people are currently doing it probably right now, everywhere in the world. Like, was that really reasoning, or was that, anyway, that's not the question of the day, but like, it goes back to, again, there's a paper by David Silver, some interesting joint at Pre-Cup and Rich Sutton, which is called Reward is Enough. And this is on my mind because I presented on it earlier this week as well, to share with colleagues. But the Reward is Enough paper is kind of special. It's worth reading if you want to get a perspective on what people who truly believe in reinforcement learning think is possible for a learning machine that's only fed a single signal of reward. That's the main thing. And the Reward is Enough paper makes the argument that everything we want from an intelligent system, if the task necessitates that capacity being built in the agent, and you give the agent reward to solve the task, it will build that capacity, given that it has sufficient resources available to it. Like, if the task requires chain of thought reasoning, and you give a reward for solving tasks with chain of thought reasoning, you should not be surprised when it builds the ability to do chain of thought reasoning, because reward will drive it to change its internal structure, its processes within the capacity it has available to exhibit that facet of intelligence, whether it's imitation or social learning or creativity or exploration, whatever it is that we consider to be so uniquely intelligent. If the task requires it, the machine has the right capacity for it, and the reward signal is driving it to solve that task, it will begin to build up the capacity. So this is neat, because it brings together sort of tabula rasa animal sensory motor learning and how we imagine maybe future iterations of all of these large models that we're seeing deployed in one way or another around the world. So yeah, I think it's a really neat connection. Any other questions? Folks, do you have like other stuff about RL? AI in general? No? You're all good?
Great, another wonderful teaching session. Thank you very much.
Thank you all for being here. Thanks so much.
Thank you so much.
We appreciate you all. Your great questions. You had really good questions, and yeah, thanks for humoring me. And I hope you remember RL. Just remember, everyone's like, yeah, it's not the cherry on top of the cake. It's not that. It is in fact a very important fundamental process of learning. So please, like, everyone's like, oh yeah, all these other big large languages. I'm like, just remember RL. It's really important. It's probably the thing that's going to be the closest thing to superintelligence. Oh, I don't have a camera.
Thank you so much.
Okay.
Thank you.